Hello.
Hello.
Can you hear me? I guess you can.
Yes.
Happy Friday. Okay.
Happy Friday.
Let me turn this down a bit. It's a little bit loud. Is that better?
No,
No?
we could hear you before, and you've done something.
How about now?
I can
Hello?
hear you, but it's not the mic. It's just your voice directly.
You can hear the mic? Okay. All right. You can hear me back there? Okay. Then it must be the mic. Are we ready?
Yeah, we're ready.
Who's ready? You're ready? Everyone ready? Ready? Okay. All right. Let's get started. Homework 3 is up, and was up actually Thursday morning. It's due next Wednesday. Um, did you have a question? No? Yes? Okay, homework 3, you should be able to do everything. So now you get to do K-maps, sum of products and product of sums and don't cares, and we'll talk about calculating static delay today, and then you get one more of these. Okay. I don't know if you've noticed, but there's an upcoming midterm. Our first midterm will be next Friday. It will be here. It covers everything up to and including homework 3 and the static delay that I will talk about today. After that, the material that I'm going to cover after static delay today, Monday, and Wednesday will not be on the midterm. Yes?
Is there a practice midterm?
There will be a practice midterm in Canvas under Files.
Is that the best way to study, or should we also go through them?
I would do both. Make sure you can do all the homework problems. In fact, before you do the K-maps on homework 3, it might be a good idea to make sure you did it correctly for homework 2. There are solutions in Canvas. Was that what you're going to ask?
I was like, if they haven't been graded yet, of course.
Homework 2 has not been graded yet. The readers have just started. There's a chance you might get homework 2 back before homework 3, but it'll be close. You will not get homework 3 back before the midterm, though. That's clear. But solutions will be posted. Any other questions? Everybody done with the lab? Yay. Okay, great. All right, lab 3 isn't due till Tuesday. All right, so let's talk about delay. We talked a little bit about this before, but we didn't actually talk about how we were going to calculate. Okay, so remember this slide? We had a mux, and A is serving as a selector here, right? And depending on A, F will either be B or C. And both B and C are 1, right? So if we change A, that shouldn't change the output. But in fact, if we looked at the timing diagram, we do see that F will go low for a brief period. And that's because each of these gates has a response time. They don't immediately produce the output corresponding to their inputs, but only after a certain amount of delay. And as a result, for a brief amount of time, both inputs to this OR gate will be 0, because this AND gate will have changed to 0 before this one can change to 1. Okay, now eventually it will, and we'll get what we expect. And this is the remember, this is what we call the settled behavior of a combinational logic, the final output. But it may take some time before that final output is available. Why am I not going? Okay. Right, so you can see all the transitions. At this point, G, let's see, because of the delay, G hasn't yet turned to 1, hasn't reached F, and so we have a 0. Okay, so if we look at a piece of combinational logic, if we change the value of an input, this is going to start changes in the logic network, and then eventually it'll settle. Okay. Now the question is when. How do we figure out when the value, the output is correct, or what we expect? And we can actually try every single value and use our knowledge about the gate delays of every gate, but that's expensive. So what we tend to do is what's called static timing analysis. And this is where we just assume that every gate will always have a change if one of its input changes. Now, you know that's not true, right? You've simulated the AND gates and OR gates, and you know that it's possible that the output won't change, even though one of the inputs does. But here we're just going to ignore that, and we don't care what logic values the inputs have. If they change, the output could change. Okay, so how do we do static timing analysis? Well, we take advantage of the fact that our combinational logic has no loops. It flows from the inputs to the outputs, here from left to right. And so we can figure out in turn when each gate will have settled and in the network, given that all of the inputs change at a particular time. Okay, so we can work this from left to right, and if we want to figure out when is the output of this gate ready, well, we need to know when its input has arrived. When is its input settled? Okay, and that depends on two things. It depends on where it's coming from. Where is that input coming from? And how long did it take to get here? So we know that the input feeding this gate is ready at time 35, but it'll take us 4 more units before it reaches this gate. Okay. So when is the output ready? Well, we also need to know about the delay of this gate. This gate will take a certain amount of time after its inputs are ready. And there's more than one input, right? So if there are 2 inputs, which one determines when the output of this gate is ready? The earliest or the latest? The latest, right? Because you can't be ready before your latest one. Okay, so we need to take the latest one. In this case, it's 39. And add the delay for this particular gate, 2. And what do we get for this one? No calculators. What? 41, yay! 41, yes. Okay, so we can do this working from left to right because we were told when the inputs are there. We can assume all the inputs are start at time 0, or if we know some of them are going to be later than others, we can actually use numbers other than 0 for them. Okay, but we can actually calculate the whole thing. So let's do that. So we need, what information do we need? we need to know how long each gate takes to respond. So here we're going to assume that's 2 units. And we need to know about the wiring. How much delay do the wires add? So that has to come from somewhere. So Vivado will know this about your design once it's placed and routed it. Okay? But before you place and route it, it would have to make guesses about these. Okay, we also need to know when our external inputs are ready. Oops, one too many. So we will assume the external inputs coming in are ready at time 0. Okay, so how many of you have heard about what's called a topological sort? Okay, so perhaps you covered that in CSE 101, where you have a directed acyclic graph. You can order the nodes so that all the nodes that have a dependency occur before you.
101 isn't a prereq, I don't think.
No, it isn't. Okay. All right. So when will the output of this NAND gate be ready? If you were paying attention, you saw it briefly, right? 3, okay. How about this one?
7. No.
No?
Yeah, it gives
Right?
not.
There's what's one gate,
Oh, okay. So
right? Even though it's inverted, it's still one gate. It's a NOR gate.
okay.
So 5 and 4, so the 5 dominates. And this one is?
6.
Yes, okay. All right, which one can we do next? Can I do this one?
You can do the OR gate.
I can do this one. I can't do this one yet because I don't have this one. So I can do this one. Okay, when is this one ready?
13. Well, they're both equal. They're both going to add up. Wait, no, 15. Wait, no. 6 plus 5 is not 13.
4 plus 7 is,
So it would be 13 total.
and 6 plus 5 is,
11. It's not 13 like I thought it was. I know how to add.
it is 13.
In total to the right, yes, but I was
Okay,
saying
that's what
11.
I'm saying. Okay. All right, how much is this one? How about this one?
That is 17.
17. Any questions? No? You understand how we're getting these?
Yes.
Okay. We are looking at each gate and asking when do its inputs arrive. So this one, let's do this gate next. This one, this input comes from here, is ready at time 17. We'll take 3 units to arrive, so it'll be here at time 20. This one comes from here, which is 7 plus 5, so this one will be 12. So 12, 20. 20 is the later one. So 20 plus the delay of this gate, which we said was 2 to keep things simple, gives us 22 eventually. Okay, this one was also 17. Okay. I guess I did this one next, I think. Yes. How about this one? 24. Okay. So this is going to be 22 plus 1, which is 23. 6 plus 17, which is 23. So this one's also 25. This one is 28. And the last one is 31. Okay. So that means for both outputs to be ready, I have to wait at least 31 units of time. Yes?
What do you mean by external inputs ready at time 0?
So the values here depend on these inputs, right?
Right.
So they're coming from somewhere. And if I want to calculate just the delay of this particular section, I'm going to assume all those inputs are ready at time 0.
Oh, at that certain time.
Yeah, it's sort of a reference. If I was doing this as part of some other logic, I might have values that tell me that, hey, input 2 is actually going to be 2 units later.
Oh, so
And I could adjust this by not making them all 0.
so the external or the outputs will always be different at every time or at a different time frame, like at time 2 or time 4.
The inputs, that's information you're given,
Oh,
okay? But we just assumed they were 0.
gotcha.
Okay, all right, so this tells me that it'll take at least 31 units. Now, if I'm not happy with that, what can I do to improve this? I have this really long wire here, 12. Maybe I could make that one shorter, yes.
Couldn't you just try and simplify the Boolean logic?
I could, might make it worse, might make it better.
Well, if you have less logic gates.
Depends how big they are.
Oh, do bigger logic gates have longer propagation delays?
They have a longer response. Okay, but what about this long wire here? You think making this wire shorter is going to help? The answer must be no, otherwise I wouldn't be asking, right? You guys know me too well. Okay, so it's important to actually identify which wires are making this slow, or where is the slowest path. And we do this, actually this comes up in scheduling, other applications. It's called critical path analysis. So basically, we want to know what are the gates and wires that are making this slow, that cause it not to be ready till time 31. So what we do is we start from the latest output and work our way backwards. We trace back and we follow the latest arriving input. If both inputs arrive at the same time, then we follow both of them, and we trace backwards. Okay, so for example, from here, this one actually arrives at time 27, this one at time 29, so we followed this one. These were tied, so we followed both of them. And so these red wires and the gates on them are on the critical path. I can make this wire 12 as short as I want. It won't change 31. In order to reduce the delay, I have to do something that shortens the critical path, or shortens every critical path, if you like. So this is actually used in making circuits faster, is analyzing which parts are slowing it down, and you know, perhaps we would look at the Boolean logic here and see if we can improve it here. Yes?
Is there something opposite of the critical path, like a term for it?
Opposite. Well, okay, so there's this notion of Slack. And Slack is not an app for your phone. Slack is an older term that had to deal with how loose a rope was, right? And when you tighten a rope, when some things are tight, you have no slack. When things are not tight, you have a lot of slack. And so we can calculate for each gate or each wire how much slack it has, how much could it be made bigger without changing the overall delay. So all of the wires and gates that are not on the critical path have some slack. Non-zero slack is called. Okay, all right. So you have one problem on homework 3 where you get to do this. Okay, this is so that you understand how this is happening. You won't actually do this in your lab. Vivado does all this for you. Okay, any questions on this?
So this is what Vivado is spending 2 minutes doing every time I hit generate bit stream.
No, it's
One of the things.
it's one of the things, but for your design, it's really not spending much time on it at all. Um, for your designs, it's really the compiling your Verilog and synthesizing it that takes the most time. If you had a really large design that filled a chip, it would take a whole lot longer to place and route, maybe overnight. Fortunately, you guys have never used more than 10% of the chip. So you think 5 minutes is long. It's not. Okay, all right. No questions on this. All right, so let's go back to our sequential design. All right, so last week we introduced the D flip-flop, and we built a few simple things: the shift register, parity checker, counters, and now we're going to kind of move on to more general design. How do we design sequential systems in general? So all of our synchronous sequential systems are going to look like this. When we open them up and peer down into them, we will see some flip-flops. And because we followed our commandments of synchronous sequential design, the clock will only be connected to the flip-flop clock inputs. And out of the flip-flops will be holding what we call the present state, the values that the flip-flop have right now. That's the present state of our system. And this present state, along with the inputs, are going into a combinational logic cloud, which has no loops. There are no loops in here. And eventually this settles. And it settles before the next clock edge comes. And it generates outputs, and it also generates what we call the next state, which is the value that will be loaded into the flip-flops at the next clock edge. Okay, so that's how they work in general. So how do we analyze the spaghetti that we perhaps see when we open it up? So let's say you're given a circuit like this with 2 flip-flops and a combinational logic cloud. So we did sequential simulations, right? But that was just for particular input. How about in general? We don't want to try all inputs, and then there's probably a really long, an infinite number of different input streams that we could think of or generate. So how do we come up with some explanation, or how do we model a sequential circuit's behavior? Well, so we have this combinational cloud, right? And this is a logic network. It has inputs and outputs, and we know how these behave. So what we do is we take a chainsaw to our flip-flops, we cut them in half, and now I have a logic network, just like we had before. And you did this before. You came up with equations for the outputs in terms of the inputs. The inputs now include the present state, and the outputs also include the next state now. Okay, so what is the equation for G here? Q1 and Q0, right? Because G is coming from this AND gate, which is being fed by Q0 and Q1. Okay, how about D1? That's a little more complicated. You know, I wired these up like these, but you don't. If you're drawing these out, you don't have to make them up. You can just label this A, and you can label this
Also A.
Q1 and Q0, or not Q1 and not Q0, or not A, so that you're not drawing spaghetti, because sometimes it's hard to follow.
You could color code them on a slide.
Okay. All right, so and then D0, I'm not going to ask you for that one. I'll just tell you what it is. Okay, so those are your equations, right? And we can make a truth table for this. But for state systems, for sequential systems, we have a truth table in a different format. It's called a state transition table. Okay. And so the state transition table is, in essence, just a truth table, but it's organized in a different way, make it a bit smaller. What we do is we list the present state as rows, but then we have different columns for the input. Okay, so here we have the 4 possible values for the present state, right? 2 flip-flops, so there's 4 values. And then we have one input A, and we have a column for A equals 0, a column for A equals 1. If I had 2 different inputs, I'd have 4 columns. If I had 3 inputs, I'd have 8 columns. We will not have too many inputs just because we can't afford many columns. Now, within each column, I'm telling you what the value of the next state is, and that's 2 bits, right? Because the next state consists of D1 and D0. So this column is the value of D1 when A is 0, and this column is the value of D1 when A is 1, and this column here is D0 when A is 0, and this column here is D0 when A is 1. Okay, and we could, of course, made a truth table that had 8 rows. You're going to find this more convenient when you have more states and more inputs. Okay, our output, G, is listed here. In this particular case, G does not depend on A directly. Obviously, A is going to determine what state you go to, and that will determine G, but immediately, G doesn't depend on A. And so we just need one column here. Right, this says that G will be 0 when I'm in state 0, 0, 0, 1, 1, 0, and G will be 1 when I'm in state 1, 1. Yes?
So if it was dependent on A, would you do something kind of like you did with the next state column?
Yes. We will do one. Yes?
In that next state part of the table, there's 4 columns.
Right, because each next state has 2 bits.
I see. So of each of those sort of subsections of 2 columns,
Right.
that's D1 on the left and D0 on the right.
Yes.
Okay. So is that the standard notation? Should I write it down in my notes like that so I
Yes.
remember that's how it looks? Okay.
You'll see why we want to do it that way. Okay. All right. So here's that same table again. All right. So as humans, we're not really good at interpreting zeros and ones. And so we often prefer to use what we call symbolic names. So when you have a table encoded in bits, we call that our encoded state transition table. And what we can do is come up with names for the states. Now here I have no idea what these states mean or what they do, so I'm going to call them A, B, C, D. When you do a design and these states have a meaning to you, you can call them Sally and Harry and Martha and Eric, whatever you want. I suggest you call them names that actually have to do with their roles. And then you can have what we call the symbolic state transition table, where we substitute the symbolic name for this bit vector that it corresponds to. So for example, 0, 0, we're going to call that state A. So over here, this is state A. And then there are several places where I have state A. This is state A, state A, state A, right? And so you can see that here. This one is state D. So all we're doing is we're translating, providing a symbolic name for these bit vectors that correspond to the state. And once we have that, we can actually then draw what we call the bubble diagram or the state diagram. So this is the most human-friendly version or view of our state system machine, because we can kind of see the flow between the different states. Okay, how do you get a state diagram? Well, so each bubble or each circle corresponds to a state. So we have 4 states, one for each A, B, C, and D. And then in this case, because the output only depends on the state, the output is written in the state. Right? When I'm in state A, the output's 0. When I'm in state B, the output is 0. When I'm in state C, the output's 0. And only when I'm in state D is the output 1.
So it's corresponding to the far left present state,
Yes.
not the next state.
No, not the next state. So in state A, it's 0. Not this one. This one. That's actually a mistake. When you're filling this, if you need to look to the far left column, sorry. All right. What about the arcs? So the arcs tell us what happens on a clock edge. They show the transitions between states that occur on a clock edge. So if we are in state A and the input is 0, we are going to stay in state A. We're going to actually just reload A into the flip-flops. However, if A is 1, then we are going to move to state B. Okay, if we're in B, we're going to go to A with a 0. We're going to go to C with a 1. If we're in C, we're going to go to D with a 0 and stay here with a 1. And in D, we're going to go to A with a 0 and go to B with a 1. Okay, so this is a direct translation of this table. It's just a different format. Sometimes, particularly if you have more than one input, it's convenient to write an expression on the arc rather than writing a value. So instead of writing a 0 here, I'm going to write an expression that evaluates to 1 when A is 0, and that's A naught. So this says if A naught is true, loop here. On the other hand, if A is true, go to B. Now, you might wonder, why do I want to do this? This is easier to understand, and it's fine if you do it either way. When we have inputs A, B, and C, or X, Y, and Z, you're going to have combinations where it's easier to actually write an expression for each transition rather than list all the possible values that cause it. Okay. All right, so what does this look like when you're staring at in the simulator trying to figure out what's wrong? Okay, so we have our signals, right? A, Q1, and Q0, and the output G. And we don't see D1 and D0 here, but they're the values that Q1 and Q0 become at the next clock edge. What we can do is then mark our simulation with the values, the symbolic name of the state. So when Q1 and Q0 are 0, we're in state A. And let's see, we had a transition here from on which the input was 1. And so we went to state B. And then here it was 1, so we went to state C. Let's see, and here the input was 0, so we went to state D. And while we were in state D, G was high. Now the important thing to notice is that if we're looking at G right at the clock edges, it isn't until we have been in D for a whole clock cycle that we see G as high. G will not be high on this clock edge. It'll be, we first need to transition to state D, and then G will be high on the following clock edge. Okay. All right, so you can see these. Any questions? No. Okay, you're going to be staring at state machines for the next 4 weeks. So, speak now. Okay, I can see. All right, so let's do another one. All right. So in this example, I'm not going to solve the flip-flops in half again. But now you can imagine that the Q0 and Q1 are coming back here. I labeled them here for you, make it a bit easier. So what is our equation for Y? Okay. All right, and we can get an equation for D1. I won't torture you with it. I'll just write them out. Okay, so you can trace through like you did before when we were just doing combinational logic and get equations for the output. Notice in this case, Y does depend on X. So this is a little different now. Before we just had the state, but in this case, Y depends on X. Yes?
So this is the finite state machine, right?
Yes.
Or so from what I'm looking at, it seems that it's feeding itself its input and adding it with combinational logic.
It's combining the current state with combinational logic to figure out both the output and the next state.
Didn't we do that for our counter, for a FIFO counter? Like
You did. A counter is in fact a sequential circuit. Okay. All right, so now when we build our state transition table as predicted, we need 2 columns in the output region because we need a column for x equals 0, and we need a column for x equals 1, right? And
Going to symbolically name the different output combinations?
sure. No, the output combinations, no. It's only 0 and 1.
Fair. Oh, I thought you said we had multiple columns.
Well,
I didn't look.
the value, okay, so each state is represented by 2 bits here. The output is still represented by 1 bit.
Gotcha.
Okay? All right, so here's our encoded state table. We're going to use the same interesting names for the states as before, and turn it into this symbolic state transition table. Everybody understand how I'm getting these?
Yes.
Anybody not understand? Anybody can't raise their hand? Okay, good. It's always good to ask the question in the sense you want the answer. Okay. All right, so let's draw our state diagram. Well, this one's a little different. Okay, so first thing to notice is that now the outputs are on the arcs, because knowing the state alone doesn't tell me the output. I need to know what state I'm in, and I need to know what the input is. So when I'm in state A, right, the output will be 0 if x is 0, but it'll be 1 when x is 1. So when x is 0, the output will be 0 if I'm in state A, and I will move to state A when the clock strikes. But I will move to B if x is 1, and the output will be 1. So it'll actually be 1 on that clock edge in the transition. Okay, so while I'm in state A, if x is high, the output will be 1, and if x is low, the output will be 0. Okay, sometimes it doesn't matter, the output's the same. For example, in state C, the output's 0 either way. And anything else you notice about this particular state diagram? Yes?
There's an island.
There's an island. There's state D. How do I get to state D?
By having state D already.
And I can only get to state D if I'm already there, right? So this should reinforce the importance of initializing your flip-flops, right? If you leave it to chance, you might wake up in state D. If I'm in state D, what will my output be?
Well, 0.
0. It'll always be 0, okay? Will I ever leave state D? No. Okay, there are much cheaper ways of generating 0 as your output. This is not the best way, clearly. So, perhaps D is kind of a leftover state. We only needed 3 states, and, because we have, with 3 states, I still need 2 bits to represent 3 different states. So maybe there was an extra combination I didn't use. So that's a possibility. What do you think, what does this look like? Anyway, these 3 states. It's a rotation. Every time x is 1, I move to the next one, right?
Except for that last one.
Yeah, I do.
Reset.
It looks like Mickey Mouse, okay. Okay, ignoring D for the moment. I have this is like a counter, right? When x is 1, you move to the next one, and we cycle around. Yes?
From C to A, is that X 1 versus the X?
So x is 1, but the output will be 0.
Oh, I see.
Right? So when x is 1, we always move to the next state, but this output is different. So whenever we're in C, we will actually have a 0. Yes?
Should we draw these in these sort of linear shapes when we draw them ourselves, or can we be more freeform? Like, could I put this in a triangle?
Sure, you can make a triangle. You're going to want to make it so that the arcs don't cross over each other. Make it as planar as possible.
What happens if the arcs do cross over each other? Is it
So if you take the graph theory course, you will learn that it is not always possible to draw it without arcs crossing over.
It's just confusing, though.
Just
so-
confusing. Okay, all right. So if you have a 5-year-old child and you want some peace or time to yourself for a good hour or so, have them draw 3 houses and then 3 circles and tell them this is gas, water, electricity. I need you to connect all 3 to all 3 houses without crossing any lines.
That's impossible, isn't it?
You don't have to tell them that.
Ah.
Okay, all right, never mind. That was a major digression. Okay, so there is a name for these 2 types of machines or outputs. An output that only depends on the current state, what the state is now, is called a Moore output. Okay, so these are legacy names. They don't get used too much anymore, I don't think. And an output that depends on what the current state is, as well as what the current input is called a Mealy output. Technically, if you have a machine where any of the outputs are mealy, then it's considered a mealy. And if you have one where all of the outputs are more, then it's considered more. Okay, but I like to think of it as individual outputs are one or the other kind. Okay, and so let's see what happens when we simulate this. All right, so here's our state machine, and we'll tell you that we woke up in state A. If I don't tell you what state we woke up in, we're in trouble because it's possible we're over here. So I'm just going to assume that we woke up in state A. We initialized our flip-flops to 0. Okay, and then the first two inputs at this clock edge, this is 0, so we stayed at A. This is 0, we stayed at A. This is 1, so we moved to B. And then this is 0, 0, so we stayed in B. Oh, wait, how did we get to D? Well, is it 1 or 0? How do we get to D?
A change on the clock edge.
We're not supposed to change the input on the clock edge, are we?
No.
No. Uh-oh. Okay. So this is a problem. Okay, so what happened? Oh. All right, so we were in state B. Q1 was 1. Q0 is 0. And then X changed from 0 to 1 very close to the clock edge. So what happened is, well, the logic evaluated and changed D1 to 1 because we wanted to go to C, right? C is 1, 0. But unfortunately, D0 didn't have time to go from 1 to 0 before the clock edge loaded these two flip-flops. So guess what they loaded? They loaded 1, 1, which was state D. That's not good, right? Because now I'm in D and I'm stuck there. Okay, so, yes?
So I know in this example, state D was not connected to any other state.
Right.
So what if state D was connected to the other states, but we changed values at the clock edge?
That might be a problem too.
Would there still be undefined behavior?
This is not undefined, this is D. Right? Okay, so the problem is that our logic did not have time to settle after X changed. Right? The clock came too early before the new values were ready. This one was trying to become 0, but it didn't make it. Okay, so how do we avoid this? Well, so if you have an input to your logic and you cannot control when it changes, you may have this problem. And one way to solve it is to add what we call a synchronizer. A synchronizer is just a fancy name for a plain old D flip-flop. So we feed our external inputs through a D flip-flop. Now, this can still change near the clock edge, but the important thing is the output will change right after clock edge. So whatever the output is, your logic will see the same value and has a whole clock cycle to settle before the values get loaded. So if X changes close to the clock edge, you may get the old value of X, you may get the new value of X, but your logic will see the same value, or evaluate the values you have will be based on the same value of X, whether it's the old one or the new one. All right, so you only need to do this if your input is coming externally from something that doesn't share your clock. If it's coming from another component that is using the same clock, you don't do this. In fact, it might cause trouble. Okay, did you have a question?
I was gonna ask if you could synchronize it with the output clocks.
The output clocks.
There's a clock of the output.
Synchronize it with.
Like have it be the same input clock for the outputs and the inputs.
I mean, this is the same clock.
Oh,
Yeah, it has to be the same clock. Otherwise, then would defeat the purpose. There's always only one clock in this class, right? Next class you can have more. Yes?
This is in regards to the Moore and Mealy outputs.
Yes?
Can you give like an example? I'm a little confused about how to categorize one or the other.
Okay. So here, the output is different depending on what the input is, right? So in this case, we get, if you're in state A, you're going to get a 0 if x is 0, or a 1 if x is 1. Right? So it depends. We need to know what the input is to figure out what the output is. Whereas if you go back and look at the previous example, when you're here, the output only depends on what state you're in right now. Now, it doesn't mean that the input isn't important. It just means that it doesn't influence you right now. Of course, it's going to influence you indirectly through what state you change into. Okay, and if we can write the output value in the state, then it's definitely more. Okay, now just because we wrote the output on the arc doesn't necessarily mean that it's Mealy, because I could have written the same output, right? If I write, instead of writing a 0 here, you could write it on the arcs. So you'd have to go check all the pairs of arcs and see if they have the same or different outputs. That's really kind of a picky thing. Because usually we'll just write it in the state if it's the same. Okay, all right, so we did that. Wait. Now I've lost my mouse. Okay.
it's in the bottom right of your. We can see your mouse on your projector. It's underneath the letter D.
Oh, there it is. Okay, go back. Oh, it's over here. That way. Okay. All right. So you only need to add a synchronizer for external inputs that are asynchronous, that don't come from systems that share the same clock. So, for example, for you, that means the buttons and switches on the board, right? We cannot hook you up to the clock and keep you from pushing the button. Okay, and however unlikely it is that you're going to get too close. All right. So what does this look like when we simulate it? So here's the original version of X. And now our system is using a synchronized version of X. This adds a clock delay. And notice how nicely it cleans it up, too. So yes, we have an additional clock delay, which is why you don't want to do this internally. And then here, when X is 1, this time we actually went from B to C instead of to D. Okay. Any questions on this? All right, so we can take any sequential circuit made up of flip-flops and combinational logic and come up with a state diagram. Hopefully it won't be too messy. But you are primarily interested in going the other direction. We have something that we want to design. How do we come up with flip-flops and logic to get this behavior? So we did the counter. And for the counter, we looked at it and we recognized there was a particular pattern. But let's forget that we understand how to build a counter. Let's do this mechanically as if we have no idea how to build a counter. Okay, so I'm only going to build a 3-bit counter. Can I come up with a state diagram for the behavior of a counter? Yes. looks something like this, right? It's 3 bits, so I'm going to have 8 states, S0 through S7. Whenever increment is low, I'm going to stay put. And whenever increment's high, I'm just going to go to the next state. And then I'm going to go back from 7 to 0. What am I going to output? I'm going to output the value of the state, right? These are my outputs. Whatever state I'm in, that's the value. And also I'm going to output this TC. TC, remember TC is only 1 when I'm in 7. Yes?
To clarify, because this just clicked, does this mean that in systems with more outputs, your input is just changing what state you're in?
Yes.
Whereas in Mealy outputs, they change both the state and the output?
Yes.
Okay, that makes a lot of sense. Thank you.
Okay, all right, so from this bubble diagram, how do I get a circuit? Okay. Well, I'm going to do exact reverse process of what we did, right? Before we started with network and we ended up with a bubble diagram. Now we're going to start with the bubble diagram and come up with our network. Okay, so here's our symbolic state transition table. Okay. We have 8 states. When ink is 0, we are staying put. When ink is 1, we are going to the next one. And when we're at 7, we're going to 0. Our output TC is 1. We also want to output the state, but I didn't list that there, but just pretend it's there. All right, it is there. I forgot it was going to be there. Okay. Don't have to pretend. Okay. So I'm going to pick an encoding now. So I have 8 states. How many bits do I need to encode 8 different things? 3. Okay. So I could pick any state encoding, but I'm going to pick the obvious one. I'm going to encode 0 with the 3-bit value for 0 and 1 with the 3-bit value of 1. And that's real convenient because whatever my state is, that's also my output, right? And so I don't have to do any work or any logic to generate the outputs. The outputs are the state values as well as TC. So I've just filled in the values. Since 0, 0, 0 is S0, this is S0, and this one is S0. So we just fill them in as before. All right, now I have to get logic. Okay, so how much time do I have? 7 minutes. Okay. So going from a logic network to an equation is easier than going from equations or, from a logic network to a table is not as complicated as going from the table to logic. Guess how we do this? It's a 4-letter word. There we go, K-map. All right, so we have a K-map for each of the next state outputs, right? We have to generate the next state, and the next state depends on the current state, Q0, Q1, Q2, as well as the input ink. So I've done it for you. These are all the prime implicants, as usual. And then we can figure out which ones are forced and use those, and we end up with those equations. Okay, this looks a little different from what we had before, does it? Well, on closer examination, can I rewrite this equation for D0? It's an XOR, right? How about for D1? Okay, I have to do a little bit more work for that, but I can, if you look at it closely, it turns out to be Q1 XORed inc Q0. Okay, to do that, I'd have to pull out the Q1.
Could you do that on the board for my benefit
You
specifically?
don't believe me.
I
Okay.
do believe you. I'm just so
No,
bad
no.
at Boolean algebra. I'm taking any chance at help I can get.
All right. Whoops. We have D1 equals inc bar Q1 plus Q0 bar Q1 plus Q1 bar inc Q0. Okay, so what I'm going to do, I get this right.
It's a bit too zoomed in to see, but I'm following along verbally. Thank you.
Okay. So we have this equation, right? Okay, so I'm going to rewrite, I'm going to pull out this Q1 here. So I have Q1 inc bar plus Q0 bar plus Q1 bar inc Q0. Any idea what I should do next? How about Q1 inc Q0? So I'm applying De Morgan's law in the opposite way that we usually do. And we have Q1 bar inc Q0. Right? So using the fact that xy bar plus x bar y is x XOR y, right? I have x bar, y bar, y. This is Q1 XORed with inc Q0. Does that look familiar?
Yes.
Yes. And guess what D2 is? So we can come up with the same equations that we spotted just by mechanically synthesizing the logic again. Okay, and we end up with this again. And any questions on this? All right, so we will, over the course of the next 2 lectures, do many more examples because you're going to be generating your own sequential systems in lab 4, 5, and 6. Okay, I'll see you Monday.